Okay, welcome everyone. So today we are looking at predicates and quantifiers. So if you are new to the channel, you can hit the subscribe button for more content like this. So we are looking at predicates and quantifiers. Predicates and quantifiers. We are still continuing on mathematical logics and proofs. So we are saying a predicate. We are just going to go and define these terms and give examples of what a predicate is and what a quantifier is. So we are saying a predicate. A predicate is a statement. Predicate is a statement. Is a statement that contains variables. This is a statement that contains variables. And for example, if I have, if I say let P of X be a statement, let P of X be a statement such that let's say X is greater than 10. And as you can see from the statement, X is a variable, right? So it's an independent variable. So we can also manipulate the statements if maybe we know the specific value of X. If X maybe is equals to 5, then we can see that P of 5 is what? P of 5 is false. Why? Because P of 5 is less than X, but the statement says P of X be a statement such that X is greater than 10, but you can see that 5 is less than 10, and it's not, and this one is not equals to, so automatically P of 5 is false because X which is 5 is less than 10, but we are looking for values of X that are more than 10. So again, if we are saying X is equals to, let me just say X is equals to 15, where now we are looking at P of 15. P of 15 is true. Why is P of 15 is true? Because we can see that 15 is greater than 10, which satisfies the proposition or the statement that we made earlier. So, and then now we are saying if we have specific values of X, or the specific values of the variables, we can evaluate the predicate to become a proposition. So a predicate becomes a proposition, when evaluated at specific values. As you can see from our case, we evaluated this statement, this predicate as two specific values, and we determined that at one specific value, which X is equals to 5, P of 5 is false because the X value is less than 10, but our statement said we are looking for values that are greater than 10, and then also evaluated X is equals to 15, and we said we've seen that P of 15 is true. Why? Because the X value is greater than 10, which satisfies the predicate that we stated. So now we are saying a predicate becomes a proposition when evaluated at specific values. What does this mean? This means P of 5 and P of 15 are now propositions. So this is the basic idea behind predicates. We are just saying it's a statement that contains variables, and then if we evaluate those variables as specific values, we get a proposition. So now let's look at quantifiers. So a quantifier tells us how many elements in a set make the predicate true. So we are saying a quantifier tells us how many elements in a set makes the predicate true. So okay, so with quantifiers, we can distinguish quantifiers in two different forms, whereby we are looking at the first form of a quantifier, which is the universal quantifier. The universal quantifier. With the universal quantifier, this is what is different. We normally use this sign. It's represented using the sign, the upside down A, whereby this sign means it means for all. It means for all. Okay, let me just give an example. If we have P of X, so what does this statement mean? This statement implies that P of X is true for all values of X. That's what this statement means, for all values of X. So this is a way of shortening. So instead of writing this entire statement, we can shorten it using this symbol. So this means P of X is true for all values of X. So let's look at another example. We look at another example where we are looking at, let's say, P of X such that X squared is greater or equals to 0. So we are saying all of the values of X here should be positive integers, or greater than 0, greater or equals to 0. So we are going to say then for all values of X, P of X is true because the square of any integer is a non-zero, right? So this one is true because the square of any integer is non-zero. It's non-negative. It's non-negative. So we can see from the statement, we are evaluating the value of P of X, where X squared is greater or equals to 0, and this statement is always true because any integer evaluated here is non-zero. So that's why we're saying this statement is always true, and we can write these. We can explain the statements using this word. So we are saying then P of X, for all values of X, P of X is true because the square of any integer is non-negative. So this is satisfied. So this is the universal. Contains a list amount. It contains a list of variables, or it contains a list of values that are included in this for all. They're included here. So now we are looking at let's look at another example of, or another form of a quantifier, which is the existential quantifier, which is represented using this sign. It's represented using this sign. So what does this sign mean? This sign means there exists or for some, if you're given a statement where there's these keywords, it's highly possible that you're dealing with existential quantifiers. So we can represent it like this. What does this statement mean? This means there's at least one value of x. There's at least one value of x in the domain for which p of x is true. Yeah, let me put it like this. In the domain for which p of x is true. So at least one, right? They exist for some values of x. This statement is true. For some values of a variable, this statement is true. So we can evaluate a mathematical statement using the existential quantifier. So let me give you an example. So this one is actually easy. If p of x such that x squared is equals to 4, so now we want to evaluate this statement using the existential quantifier. We can say, based on what we're given, we can say for some values of x, p of x is true because they exist integers x is equals to 2 or x is equals to -2 that satisfy the condition x squared is equals to 4. So you can see now it's not all values of x, just like the universal quantifier, but now we are saying we're looking at specific values of x. There are some values of x that satisfy this condition, and in our case there are 2, because we know that 2 squared is equals to 4 and also -2 squared is equals to 4. They satisfy this condition. It's not all values, it's not all integers or all natural numbers that can satisfy the statement, but only some, or they exist a few that can actually satisfy this condition. So this is all. So this is the basic information about universal quantifiers and existential quantifiers. Just an intro, and we are going to dive more deep into this later on when I'm doing other videos. So this is all for today.